So for today, we're going to start by looking at some exponential growth. We've already looked at this compound interest formula, but we only did it with our graphing calculator, where we typed in one side of the equation with y1, the other side with y2, and found out where the two graphs intersected. Today we're going to look at a more algebraic approach. Some of the questions are going to be really straightforward. Determine the final value of $500 after 10 years if it's invested at a rate of 2.25% interest and compounded monthly. So we just need to plug things into our formula. We want to find the amount. The initial amount was 500. That's your principal. Your interest rate, you change it to a decimal. The fact that it was compounded monthly means that the end value will be 12, and it's over 10 years. All of the numbers are all together. You can type this into your calculator as exactly as you see it and get an answer. So I want you to try the second one. Here you can check how you did. So those first two examples were really straightforward, just plugging things into your calculator and figuring it out. The next ones we look at is these ones where it says calculate the time for a $30 investment to double if it's compounded at a monthly rate of 7%. Now, if you remember that day that we did the rule of 72 or the rule of 70, if we take 70 divided by 7, we get 10. And the rule of 70 or the rule of 72 is a way to estimate how long something's going to take to double. So we would estimate that it's going to take about 10 years. Setting up our equation, if it doubles, it starts at 30. It's going to go to 60. And now we're solving for t, and t is in an exponent. So this is an exponential equation. And how do we solve exponential equations? We solve exponential equations with logs. But before we get to the logs, you're going to find that whenever you have a number in front like this that's multiplied by something else, it's going to be easier if you divide first. I don't know if easier, just a little bit less work. So if I divide both sides by 30 first, then I'm going to get 2. 2 is equal to 1 plus 0.07 divided by 12 to the 12t. And the interesting thing about this that comes out of this is that it doesn't matter if this was 30 and 60 or 30 million and 60 million. When you divide, you're going to get 2. And that means that no matter how much you start with, it's going to take the same amount of time to double. And if we figured out 10, that 70 divided by 7 is 10, this is we're thinking it's going to take roughly 10 years to double. So if you can find someone who's willing to give you $30 million just for 10 years, it's hard to find these people. I've been trying. You could double that money and then give them back their 30 million, and you would have 30 million as well. But to find someone who's willing to do that, that's the tricky part. So now we can take the log of both sides. Does it make sense that this exponent can come out in front now? And that's the reason we do take the log of both sides. We want to get the variable out of that exponent. Once that variable is out of that exponent, you can now get t by itself by dividing by 12 and log of 1 plus 0.07 divided by 12. Put that all into your calculator and check. Our estimate was 10 years, and it's actually really close to 10 years. Now, plug everything into the formula for this one, and we want to find out how much he initially invested. Question here, is this an exponential equation? There's exponents, but an exponential equation is when what you're trying to solve for is in the exponent. But what we're trying to solve for isn't in the exponent. So we won't need logs for this one. In fact, to get p by itself, all we need to do is divide both sides. And then again, it's just being able to type that into your calculator and see if you're able to get the same answer. So I want you to try the next two. First of all, we set up our equation. That's no problem. And now walking around, I saw two different techniques. I've got the technique that we haven't done as often up on the board, but I saw a lot of people divide both sides by 200 first and get 2.5 on the left. That's perfectly fine. That's great. I'm going to do this one as what happens when you say, I see that I'm solving for t in the exponent. I know I have to take the log of both sides. What if you do that right away? What if you start off by saying, I take the log of both sides? The temptation with this, if you don't divide first, the temptation with this is to bring the 4t out in front right away. But you have to be careful because that exponent is just to this set of brackets. That 4t does not apply to the 200. The 200 is multiplied in front. That's why I put that green dot there. So we have to first use our log law that says when you multiply, you add. And so you get log 200 plus, and then log of this, and that's when that 4t can come out in front of your log. So when you don't divide at the beginning, it's not wrong, but then you have to remember to use your log laws for multiplying first before you can bring that exponent out in front. Now that you've got your exponent out in front, you can use your skills to try and get t by itself. I'm going to subtract log 200 on both sides. And now I can divide both sides by the 4 and the log 1 plus 0.03 divided by 4. Plug that whole thing into your calculator, and whether you use the other method or this one, you should get 30.66 years. Look at the top of the fraction. If you did it the other way, was the only difference in your final fraction the fact that you had log 2.5 at the top of your fraction? Yes? And if we look at that top of our fraction here, can you see that you could use your log laws to combine that? How do you combine logs if you're subtracting? You divide. And then you get the 500 divided by 200 and the 2.5 that way as well. So that shows a little bit why they're equal. Again, you have to write a lot less logs if you divide at the beginning as well. So it makes your work a little bit more concise, which is nice. How many people have finished the next one already? Couple? Okay, I'll give you a little bit more time. So for this one, it doesn't tell you how much. So you could pick any amount for starting with. If you picked $1, you could say how long does $1? You could pick $10 and 30. Either way, once you simplify it, you're going to get 3 equals. And then when you take the log of both sides, 12 can come out in front. Get t by itself. If there's a rule for 72, I wonder if there's a rule of something for tripling. But I don't know what it is. Solving for t, did you get 22 years approximately? So our compound interest formula, sometimes we have to solve for time, and now we can do it algebraically, whereas before we just did that graphically. Use, when you have lots of things in your fraction, use your fraction button. Try it again. So now we're going to look at another formula. Again, on your exam, if you're given any of these questions, the formula will be given to you. They'll give you the formula. They find that that way your formula sheet isn't super full with formulas. It also means that on your exam, you could get any type of formula and have to be able to use it. So here's another formula, and this formula is for when things grow continuously. Now, we looked at compound interest, and that was when it was compounded monthly, or if it was compounded daily. And the question is, what happens if you did it more often, so that eventually it would be compounded continuously? The interesting thing is the formula, if n is a really, really big number, turns out to be this. And the n goes away, and the number e appears. R is still the interest rate as a decimal, and t is still the time. So what would that mean? Well, we're going to look at an example here. We're actually going to do part B first. You have $2,000. What would happen, how much would it be worth if he had 5.5% interest and it was compounded quarterly? So you plug things into your formula. And in 10 years, that $2,000 would be worth $3,453. What does compounding quarterly mean? That means they're figuring out the interest rate in a year. So 5.5% interest on $2,000 would be $110. $110 a year. And they say after 3 months, we will give you a quarter of that. And then 3 months later, we'll give you a quarter of that, but we'll also give you some interest on your interest. And so compound interest, you make interest on your interest. And if it's compounded quarterly, that happens 4 times in a year. So now if we were going to do that continuously, that means every second, or even more than every second, the bank is putting a tiny little bit of money in your account, and you will be making interest on the next second off of that money that they put in. So your amount is going to be more. How much more? And I think you're going to be surprised by this. Are you ready? This is 10 years. In 10 years, it's going to be, oh, drama, $12 more. You're probably expecting a huge number, right? It's kind of disappointing. Now, no banks offer continuous interest rates that I know of, nor do I know any banks that say they're going to charge you continuously, because that would just make people mad, because you would expect it to be a lot more, and it's not a lot more. The biggest thing that's going to affect how much money you're going to pay a bank, because someday you're going to pay a bank money, unless you decide never to borrow money from a bank. And that would mean that you probably never own a car or never own a house, because those things, chances are you're going to have to borrow money if you want to get them. The biggest thing that's going to affect how much it's going to differ is the interest rate. So when you're borrowing money from a bank, it will be worth your while to do research to find the lowest interest rate possible. Because even a small change in the interest rate can make a huge difference. And when we look at that on Wednesday, we'll really see some big, big differences. But the amount of compounding periods, it does make a difference, especially over time. But you see with this one, only $12 over 10 years is not a lot. I mean, you're going to be $12 richer. So in 10 years, what do you think you can buy with $12? What will cost $12 10 years from now? Maybe you could get an extra value meal somewhere for $12. Okay. So the key to knowing when you're going to use this PERT formula, as I like to call it, is whenever the question says continuously in it. So if something is compounded continuously, that's telling you that you're going to have to use this continuous growth formula. And again, your questions will have that formula built into it because it's no longer on your formula sheet. In this case, what we're trying to solve for, the interest rate, is in the exponent. So this is an exponential equation. How do we solve exponential equations? We're going to have to take the log of both sides. Before we do that, though, since we're multiplying by 200, it's going to make our life a little bit easier if we divide both sides by 200 first. And you don't have to simplify that fraction. You can if you want, but you can leave it as 235 over 200. And now, since the base is e, you could take the log of both sides, but I'm going to take the natural log of both sides because all the rules are going to be exactly the same, whether you use log or natural log or any base log. But the nice thing about using natural log when your base is e is the natural log of e is equal to 1. So when I bring that 3r out in front, this part right here is equal to 1. And then to solve for r, all I need to do is divide by 3. Plug that into our calculator and you get 0.0538, which is 5.38%. Well, you can check how you did. And as we go to the next page, we'll look at populations. So I would use my fraction button, type that in the top and that in the bottom. See if it works. Because it should. So compound interest isn't normally compounded continuously. So the PERT formula is more often used for populations, especially in populations where it appears that population is big enough that a continuous growth model makes sense. And human populations are quite big, so a lot of times a continuous model does make sense. So if we have our PERT formula, and here it's growing continuously at a rate of 1.7%, we want to find the projected population in 2011. Well, that's just a matter of plugging everything into our formula. And there's no logs to use here because we've got only numbers on the right-hand side. 2011 would be 30 years after 1981, which is given in the question of when we had 1.38 million. And once you round it to the nearest tenth of a million, you get 2.3 million. Now in part B, it says when will the population reach 6 million? So when we go to set things up, and are you okay with me using 6 instead of 6 with a whole bunch of zeros? And then changing the 1.38 million to 1.38? And since we're multiplying again as a first step, if we divide both sides by 1.38, it's going to make our life a little bit easier. And then the base is e, so we can take the natural log of both sides. Again, the natural log of e is equal to 1. So all we would have to do is divide by 0.017 to find out t. T is 86.5, and that would be 86.5 years after 1981. So then it would be sometime in the year 2067. So for our last example, everybody ready? Well, if we go back to the actual question, it says when. So if you wrote 86.5 years later, or you have to somehow have the reference to 1981 in there, right?
Did we use the stat from 2011?
You could use the stat from 2011, but then we wouldn't put 1.38 in. You'd put the 2.3 in. And, well, you would want to put in the number that wasn't rounded. Because anytime you round early in a question and carry that rounding through, your final answer is going to be off a little bit. So in this case, using the 1.38 is better than using the 2.3 million, but your answers will come out the same. Your t will be less. It will be 56.5 because it was already 30 years later. But both of those values will work. So in this last question, we've got a population of a herd of gophers. When it was first studied, there was 15,000 gophers. 6 years later, the population was 18,000. How long would it take to triple? So if we think of our continuous growth formula, we want to solve for t, because it says how long. In order to solve for t, we need to put in things for everything else. Do we know a? Do we know p? Do we know r? We don't know r. So we want to find out how long it's going to take, but we don't know r. So the very first thing we have to do is find r first. Do we have enough information to use that formula to put everything in, so the only thing we don't know is r? Yes, because we know 6 years later it went from 15,000 to 18,000. Now we're solving for r in the exponent. So we're going to use logs. First of all, I'm going to divide both sides by 15,000. Are you okay with me taking off the zeros and just writing it as 18 over 15? Could be reduced further, but that's okay. And now since the base has a base of e, I'm going to take the natural log of both sides. And solving for r, I get natural log of 18 over 15 divided by 6. Here is the approximation for r from my calculator. I kept the dots to say that I'm going to keep all the decimal places. So I'm going to go to my calculator. I'm going to type in natural log of 18 divided by 15, all divided by 6. I'm going to push enter, get that value, and I'm going to store all of those decimal places, and I'm actually going to use the letter R for it. We normally use X, but since it's already got a letter, it's going to be easy to remember. So how do I store as a different one? I use the alpha key, which gets me to all my letters, and R was above the X. So now I've kept all of those decimal places and stored my value as R. Once you have your R value, right, we can say, well, what were we originally trying to solve? We're originally trying to solve for t. We didn't solve for t right away because we didn't know R. Now that we found our R value, now we can find our t value. Now the biggest question that students have at this point is, well, I want it to triple, but should I use the 15,000 or should I use the 18,000? Okay? And the truth is it won't matter. Because if you use the 15,000, you'll triple it and you'll put 45,000 over here. If you use the 18,000, you'll triple it and put 54,000 over here. Either way, when you divide to begin with, you're going to get 3 because it's tripled. So no matter what number you use, because it's tripled, you're going to get a 3 there, and then you can solve. And since we're solving for something in the exponent, we're going to take the log of both sides. I'm going to use the natural log because my base is e. And again, all the way through, I'm showing that I'm, with a little dot, dot, dot there, I'm showing that I'm keeping all of my decimal places. And then when I go to type it into my calculator in the end, I need to get my fraction button out. The natural log of 3 divided by r, so I can go alpha r. And it's 36.15 years. So I'd like you to do the last one. The last one is very similar. So there you can check, did you get 28.56 years? Excellent.